power. 9 to the 3/4. Cannot minimize. That's fine. So in order to solve this, because conventional wisdom would say, oh, let's just plug it into a calculator, which you could do. It's going to involve some decimals, but understand this comes from the SAT section of mathematics where you're not allowed to use a calculator. Okay, this covers what's known as rational exponents. We're going to use the substitution property of equality, which states if two things are equal, we can substitute it in. Then we're going to use power of a power when it comes to exponents, and then rational exponents. So, first thing, substitution property of equality says that since this is 9, and I know that 3 squared is equivalent to 9, I can plug 3 squared in and rewrite it as 3 squared to the power of 3/4. Then, with the power property of exponents, okay, or power of a power, states that in this case, anything to an exponent raised to another exponent, the exponents are multiplied. So 2/1 times 3/4 gives you 6/4 or 3/2. So this is equivalent to 3 to the 3/2. Okay. Now the next property of exponents states that we could have a power property of exponents, which allows us to break this up. Okay. I'm going to break this 3/2 into 3 to the 2/2 times 3 to the 1/2. Okay, 3 to the 2/2 is going to simplify just down to 3 to the first power, okay, or 3 by itself. Power property of rational exponents allows or states that anything to the 1/2 power is equivalent to the square root. So from this, following the chain of work, your answer, the equivalent answer is 3 times the square root of 3. Okay, which would correspond to answer D. That's the algebraic method of solving. Very handy to know because if you know anything about the SAT, it breaks your mathematics section into 2 parts. One is with a calculator and one is without a calculator. Like I said, your self-eval, as long as you get it to me by tomorrow, you're going to be good. Today's lecture is going to be pretty short. We only got about 21 slides to go over, so you'll have a little bit of time to knock that out. And then you'll have your homework, just the things that are going to hit the grade book tomorrow, bell work, lecture notes, self-evaluation, and the mastery check from over the weekend if you haven't gotten that done. But as long as you can beat me to the grade book, you don't get a missing sign. Okay. So our 5-minute review covering items from section 2.1. Remember, we were identifying functions. We were trying to determine if they are one-to-one, onto, or both, or neither. We also evaluated a little bit of function notation there. So if you remember correctly, an onto function means that each item of the range, which would be our y value here, is associated with each item or an item of the domain. Okay, it doesn't have to be a unique item. So most of the functions that we deal with are always going to be onto. The key fact is that when we're dealing with one-to-one functions, we should be able to draw a horizontal line across our xy plane and only intersect our graph once. So in this case, we really want to look, since it's given to us in a table and we don't want to spend time graphing it, we want to look if there are any duplicate y values. Okay, so 1346, 1240, 1446. Right there, this point and this point would fall on the same horizontal line that we would draw. Okay, so what that means is that it's not one-to-one, but since each item of our range is paired with an item of our domain, it is an onto function. To determine if it's a function in itself, it would have to pass the vertical line test, which means we're going to be looking for duplications of our x values. Okay, so there's no duplication. This is a function and it is onto. Okay, here, determine whether a relation is a function. So first question, does it pass the vertical line test? Do any of these grid lines that work up and down intersect the graph more than once? Answer to that is no, so it is a function. Okay, now is it one-to-one or onto? You can see pretty clearly that the x-axis intersects the graph twice. So that means that it's not one-to-one. It appears that each item of the range is paired with an item of the domain. So this is also going to be an onto function. Okay, here they give it to us in ordered pairs. Remember, the x values come first, y values come second. Make sure I'm recording this. Okay. So determine whether the relation is a function. If it is a function, determine if it is one-to-one, onto, both, or neither. So first question we want to ask ourselves, does it pass the vertical line test? Or can we say that this relation is a function? So vertical line, we want to pay attention to our x values. So here we have 1, 2. Okay, that's fine. 2, 1, that's fine because x value, y value. 5, 2, x value, y value, that's cool. 2, 5. Right there, we know it's not a function. Because if we were supposed to plot this on an xy plane, we'd go to the x-axis, we'd go to the right 2 of the origin, we'd go up 1. But then when we're plotting this point, we'd find x value 2, go up to 5. That intersects in one vertical line, stating that this is not a function. So since it's not a function, it can't be one-to-one and it can't be onto. Right there. Pretty simple, pretty easy. I know it's stuff that you already covered, but we want to make sure I pound this into your guys' head. That way we never have to come back to it. So find f of 3 if f of x is equal to x squared plus 3x plus 2. So f of x squared plus 3x plus 2. Okay, this is what centers around function notation. It's a big thing once you get to like calculus and pre-calc. All of your equations are written in function notation. They want you to evaluate it for f of -3. Remember that wherever we see an x value, we want to plug in our -3. So we have -3 squared plus 3 times -3 plus 2. Okay. Order of operations, take care of your exponents first. -3 squared is 9. 3 times a -3 is -9. Plus 2 stays. 9 minus 9 is 0 plus 2. Therefore, f of -3 is equal to 2, which should correspond to letter C. Have the bad marker. Okay, looking at our final check, says what is the value of f of 3a if f of x is equal to a -2x, or f of x is equal to x squared minus 2x plus 3. It's minus 2x. Change that. Be nice if they just use the same equation. We want to find f of 3a. All right. So evaluating the function again, remember the whole key is whatever is on the inside of the parentheses gets plugged in for each value of x. So f of 3a in all reality is 3a squared minus 2 times 3a plus 3. Okay, this square has to apply to both terms. So 3 squared is 9, a squared is a squared. 2 times 3a is -6a, and then plus 3, because nothing adjusts the constant. That is our value for f of 3a. 9a squared minus 6a plus 3 corresponds to letter D on the slide. All righty, now let's get into some new stuff. So we have analyzed the continuity of functions. Remember, if it's a continuous function, we can draw it without ever having to pick up our pencil. Okay, now we're going to identify linear and nonlinear functions by examining equations or graphs. We're going to determine what graphs of functions have line or point symmetry. So here you have your new vocabulary. You have linear equation. Simply put, it can be written in y equals mx plus b. That corresponds to a linear function. Okay, a nonlinear function is all other functions that do not fit the form y equals mx plus b. You have line symmetry and line of symmetry. So when you're thinking about line symmetry, we want to think about folding a burrito in half or folding a piece of paper in half. Okay, we're going to try to draw a vertical line that allows us to fold the graph over upon itself. Okay, for point symmetry, it's still the same type of symmetry, except for instead of drawing a line and folding it on top of itself, we're going to rotate our graph 180 degrees about a point to have point symmetry. Okay, so line symmetry is the concept. The line of symmetry is what divides the graph. Point symmetry is, again, the concept. The point of symmetry is a specific point on the XY plane that we can rotate our graph around and it maps onto itself. And I'll show you guys a couple examples of that. So first thing, key concept, linear functions. A linear function can be written in the form f of x equals mx plus b or y equals mx plus b, where m and b are real numbers. And then you have some examples of what are linear functions and what are not. Okay, so the first one, f of x equals a negative 2/3 x minus 1, once again fits the form mx plus b. Okay, f of x equals 1/2 x would fit the form y equals mx plus b. 4x minus 5y is equal to 16. It would take some algebra to get it there, but it would. Okay, and I'll even solve it for you. Waste a little bit of time. So 4x minus 5y is equal to 16. Once again, to get it into form y equals mx plus b, we're just isolating the y value. Okay, so the first thing we would do, subtract 4x from both sides. We'd be left with a negative 5y is equal to a negative 4x plus 16. Then we divide both sides by negative 5 and be left with y is equal to 4/5 x minus 16 over 5. Here's the form y equals mx plus b. Okay, a couple easy ways to remember linear functions. Okay, especially because they're always going to give you, to you in different ways. It's going to be a table, it's going to be kind of a problem, it's going to be a graph. Okay, if it's a linear function, you can draw a line to connect all points. Hint, hint, wink, wink. That's why it's called a linear function, right? You can draw a line. Second thing, okay, there is always a constant rate of change. Okay, or rate of change, common term is just slope. Okay, it doesn't bounce between x values. It always increases by the same exact amount each and every time. The third thing, the x variable will always be to the first power. Okay, so that's just x to the first, which is just x. You're not going to see x squared, x cubed, square root of x, all of those are not linear functions. Those are nonlinear functions. X to the fourth, once again, the exponent will always be to the first power, or it'll just be stated as x. Okay, so 3 ways that you can remember what a linear function is outside of that it'll fit the form y equals mx plus b. Okay, because sometimes they're going to give it to you in a graph. If you can draw a line to connect all the points, there's always a constant rate of change. You can identify that linear function faster than rather than having to write a linear equation for that function. Okay, going through some of these non-examples, I have f of x is equal to the 1 over x. I know it looks like that x is to the first power, but once again, due to the properties of exponents, 1 over x is equivalent to x to the negative first power, so that really wouldn't fit. Also not going to have a constant rate of change on it. The second one, 2x plus 6y squared equal to negative 25. If we were to take this and to solve this, we would subtract negative 2x from the left side to get it to the right side. We would have to divide by 6, but then we would have to take the square root. Okay, because we have to take the square root there, it's not going to work. Okay, and then x plus x y, x plus x times y, geez, is equal to a negative 5/8. Once again, when we're trying to solve it, we'd subtract x from one side to the other, but then we would have to divide by x. That would cancel out to be a negative 1, so we would just have a constant function. I mean, that one, it's a horizontal function, it has no slope or anything like that. Could be claimed a linear function, but not really. Okay, it's more of like a constraint type thing. But when you're identifying linear functions, the first part's is very easy. Fitting into y equals mx plus b. So state whether each function is a linear function, write yes or no, and explain. So we're given a is equal to g of x, which is equal to 2x minus 5. So ask yourself, does that fit the form y equals mx plus b? The answer to that would be yes. Our slope is 2 here. Our y-intercept would be negative 5. So this is a prime example of slope-intercept form. Okay? So we're going to identify them by equations. Where m is 2, b is negative 5. M is your slope, b is your y-intercept. Okay, the next one, state whether each function is a linear function, write yes or no, explain. So part of the requirements of having a linear function is that the x variable is never to a different exponent besides 1. Here we have x cubed. Okay, that in itself ruins it being a linear function. This is nonlinear. Okay, it can't be written in the form y equals mx plus b. And it's also because x has an exponent other than 1. This last one, 3y minus 21x is equal to 12. Okay, in order to work this, to really figure out if it fits the form, it's going to pass one of our tests that our x is to a single exponent. So it's equal to 12. Okay, if we want to solve it, we would add 21x to both sides. To get these to cancel out, you'd be left with 3y is equal to 21x plus 12. At this point, we could declare it's a linear function, divide everything by 3. We'd be left with y is equal to 7x plus 4. Okay. Ways that you can pick it up, this is what's known as the standard form of a linear function. This 3y minus 21x is equal to the constant. It's another way that you can write a linear function. But if you're ever in doubt, try to work it to where you isolate the y variable. And if you're doing your algebra correct, you'll hit you'll hit slope-intercept form, which is the form y equals mx plus b. X doesn't have a different exponent than 1, so this passes all the tests. So yes, this is a linear function, okay, with a slope of 7 and a y-intercept of 4. Okay, so here, Melina and Helena work part-time at a smoothie store. First, the number of hours they worked increased for the first 5 weeks on the job. The graph models Melina's weekly earnings, and the table models Helena's weekly earnings for these 5 weeks. State whether each relation is a linear function and explain. Okay, so here we have Melina's. And one of the first requirements of being a linear function is that we could draw a single line and intersect each one of their points. Okay, that would pass. The second is that there is a constant rate of change. So what that means is as they move week to week, the earnings, they increase by the same amount. So from week 1 to week 2, she made $30. She went from 90 to 120. From week 2 to week 3, she went from 120 to 150. So that's 30-30. That works out. From 3 to 4, 150 to 180. That's 30-30-30. And then from week 4 to week 5, she went from 180 to 210. So because you can draw a line through it and hit all of the points, you can also have a constant rate of change between weeks and earnings. Melina's is modeled by a linear function. Okay, from those two items, we don't even have to really write a linear equation for this. Okay, so now let's look at Helena's. So from week 1 to week 2, she increased by $60. Okay, from week 2 to week 3, she went from 120 to 180. That's another increase of $60. So her first 3 points do have a constant rate of change, but then week 4 throws a problem in. She only increased by $30. So 180 to 210, and then from week 4 to week 5, she only increased by $30. So it's like hers started off and then it leveled out. So linear functions don't do that because they have that constant rate of change. Okay, if we were also to plot this in a point, a single line with the same slope isn't going to intersect all of these points. And they do a pretty decent job of showing that on the next slide. So it is a linear function. A straight line can be drawn through all the points for Melina. That was the graph that we were looking at. The table is not a linear function. The x values in the table increase at a constant rate. However, the y values in the table do not increase at a constant rate. So if the points were graphed, a line could not be drawn through the points. And here is an example of Helena's earnings. So you can see here's her $60 increase from week 1 to week 2, a $60 increase from week 2 to week 3, but then it kind of gets cockeyed. Okay, it kind of gets bent down and starting to level out. So that our one line would be intersecting here for those points, but then we'd have to develop a new line to encompass those other 2 points. So that just doesn't work for us. That is not a linear function. Okay, line symmetry and point symmetry. Okay, I'm going to go to the book. This is shown on page 97. I like this example because it shows you what actual line symmetry would look like. Okay, so it says a vertical line divides the graph into 2 images. So if we're looking at this parabola right here, this grid line that I have my cursor on is right through the vertex. It's right through the extremal point, however you want to look at it. But if we were to draw this vertical line, you could see we would have this portion and this portion of the graph. If we were to fold these over, we would have what's known as line symmetry. Okay, so the vertical line divides the graph into images. Okay, the way that you want to be able to check is if you have line symmetry. So I'm going to put an equation up here. We'll go f of x is equal to x minus 1 squared. Okay, putting an equation up there, it's equal to f of x is equal to x minus 1 squared. This will be a parabolic shape. This will also have line symmetry, but I want you to be able to recognize it outside of just having the graph. So first thing, I'm given the equation. So I need to plot some points so that I can actually graph it. Okay, 1 minus 1 is 0, squared is 0. 0 minus 1 is negative 1, squared is 1. Negative 1, that's negative 2, squared is 4. 2 minus 1 is 1, squared is 1. 3 minus 1 is 2, squared is 4. So I'm right there. All right, that's good enough. If I wanted to draw it perfect, it would take me hours. So here we have a parabola. Here's my point, 1, 0. Okay, and I want to say that this graph has line symmetry about the line x equals 1. Okay, so my dashed line does do a decent job of dividing it in half. I do end up with two separate sides. I have the left side and I have the right side. And it looks like if I were to truly fold this over, yes, they would map onto themselves perfectly. Okay, the way to check this to be 100% sure is to double check wherever you have line symmetry. Okay, and you can just pull these points off of the graph. You don't necessarily have to plug it in. Here is where I think I have my line of symmetry. Okay, right there at 1, 0. If I look, I have my x values to the left, I have my y values to the right. Okay, if I look from moving one space from this line of symmetry in either way, I should get the same y value. So I started at 1, that's where I think my line of symmetry is. If I move 1 to the left, my y value I get is 1. Okay? If I start at 1 and I move 1 to the right, the y value I get is 1. That shows that I'm having line symmetry. Okay? The farther away that I'm moving from the line of scrimmage, or not line of scrimmage, line of symmetry, it should be equidistant, but they will have the same y values. Okay? With a parabola, it's called the axis of symmetry. It's half the reason why we graph them this way. So starting at 1, if I move 2 to the left, I get the y value of 4. Starting at 1, if I move 2 to the right, I get the y value of 4. So all of these, plus the graph, I can get a pretty good estimate of the graph, but then I can always build this table to really be sure. Okay, and to double check myself in regards to line symmetry. In other words, the y values will be the same, but your x values will change. Okay, so now let's look at the books example. Okay, so here we're given a graph. It looks like it's a quartic function. It has 3 turning points with a positive a value. So should have line symmetry, but it's a matter of where it is. Okay, so I think that if I were to divide the graph at this y-axis and then fold this side on top of this side, I think that it would match up perfectly. So that's about y equals 0. Okay? So or x equals 0 as my line of symmetry. Okay, now to double check myself, just to make sure that I'm right, I'm trying to find some grid points. And it looks like I have 2. 2 that could help support it. Okay, the first one being -1, 0 here, this point. Okay. 1, 0. The second point on the left-hand side that I would choose is -3, 0. Right there. So now, if I compare it to my other side, and I think my axis of symmetry, my line of symmetry is right here on the y-axis, and I went 1 left and got the point of 0, and I went 3 left and I got the point of 0. So if I go 1 right, I do have the point 1, 0. Okay, so now if I go 3 to the right, bang, 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 I do end up with 3, 0. So based upon this and a little table that I've drawn on the board, just basically writing down notes that as I was explaining it, here's where I think my line of symmetry is. Here's the 2 points that I picked to the left. Here's the 2 points that I picked to the right to see if they mapped up. Okay, I moved 1 to the left, had the y value of 0. Perfect. I moved 1 to the right, had the y value of 0. That checks off for line symmetry. Moved 3 to the left, still had a y value of 0. That's okay. I moved 3 to the right, still had the y value of 0. So all of those support my conjecture that this graph has line symmetry about the y-axis. Okay, so we're identifying where we think the line of symmetry falls, and then we want to try and support it. Okay, I'm not going to ask you to build the table. They just ask, does it have line symmetry or does it not? Okay, if it does have line symmetry, we need to give a line though. So the graph has line symmetry. The line can be drawn through the center of the graph, and the graph will be identical to the right and to the left. So at x equals 0 or the y-axis, so you can fold the graph on the y-axis, the graph will map onto the same line. So the answer is yes, the y-axis or x equals 0. The key thing being line symmetry is all about vertical lines. Okay, you cannot draw a horizontal line and have a function that has line symmetry. One, because that would break the vertical line test to begin with. Okay, so now we're looking at point symmetry. Okay, point symmetry, if we look at the example in the book, because I think it does a better job of explaining it. Okay, so it'll have point symmetry if it can be rotated 180 degrees about a point so that its rotation maps exactly upon itself. Okay, so if we're looking at this cubic function here, okay, if we look at the point 0, 0, okay, so that's the point at which I believe it has point symmetry. The graph, if I turned it over 180 degrees, it looks like it's going to fall right upon itself. Right, this one's easy because it's about the origin. So, but what I would do to double check myself is I'm going to try to find a grid line where I don't have to estimate, and it looks like I have one right here. So that point is at -2, -3. Okay, and remember I said that I think it's at 0, 0. -2, -3, double check. 1, 2. Perfect. Okay, so now with point symmetry, if I was left, I went left 2, I had to go down 3. So if it has true point symmetry, I should be able to go to the right 2 and up 3, and I should be able to find the same point. Boom, I have it right there at the point 2, 3. Okay, this one's not a very good one because I only have 2 points that I can map to each other. Typically, you'd like a little bit more, but we can prove it just with these 2 points. So once again, this was the point that I thought I had point symmetry at. 0, 0. Okay, that's the point which I'm going to rotate it around. From this point, I went to the left 2, and I went down 3 to find 2, -3. If it has point symmetry, I should be able to do the exact same thing, just in the opposite directions, to find that it has point symmetry. Or in other words, if the given point is xy that I picked out, right, the given point would be xy, it'll have point symmetry if you equal negative x, negative y, or the opposite. Okay, this was negative 2, 3. I go to the opposite for both my x and y values, I get 2, 3. Okay, if it has point symmetry, this only works about the origin. So, this only works about the origin. I'll show you the way that you do it when you think the point's off. Key thing is we're counting to the left and counting to the right of the point at which we think it works. That one checks out. Okay, we have point symmetry there. The opposite rule only works if it's about the origin. Okay, so don't get in the habit of doing that. That's the definition of an odd function. Okay, but if we look at this point. So here, I have a graph. Once again, I want to try and find a point where I believe if I were to rotate it 180 degrees, I would map on top of itself. And the point I'm choosing is 0, 2. Okay, 0, 2 right there. Falls pretty nice. Now I'm going to be searching for actual grid points where I can find. Where I have points that fall on grid lines. That way I do not have to estimate. Looks like I have one right here. That's 1, 2, 3. So that is to the right. 1, 3. Okay, working to the left. This point to this point, the relation is 1 right, 1 up. So if I have point symmetry, I should be able to go 1 left, 1 down, and fall upon a grid line. And I do. Negative 1. Okay, point symmetry is a whole lot harder to prove, especially when it moves around the graph. It's pretty easy and it's pretty simple when you're talking about the origin, but you'll cover that once you're talking about odd functions. The key is, here's the point of symmetry. You want to be able to find that point first. Okay, and we want to know what we had to do to get to this point. So 0, 2 compared to negative 1, 1, I had to go to the left 1 and down 1. Okay, if it has point symmetry, then if I do the exact opposite, so to get to this point, if I go to the right 1 and up 1, so from 0, 2 to 1, 3, if those both fall upon the graph, I have point symmetry about that point. Okay, that's a key thing because it's not going to be enough to just say, oh yeah, it has point symmetry. You have to label the point of symmetry. So you get a good estimate and then you check yourself. Once again, here's the point of symmetry. Here's that 1, 3. You can see it fell on upon a grid line, so that made it easy. Here's negative 1, 1. Had to go up and right 1, had to go down and left 1. Since those check out, that proves that I have point symmetry. So the graph has a point of symmetry, which we can rotate the graph 180 degrees, and the graph will be identical. That point is at 0, 2, so we would answer yes, 0, 2. So that is